Hi everybody. In the previous lectures, we have seen what is a space, what is an Hilbert space, what is the basis and dimension or rank of a space, then what is a draw as per Dirac notation, Ket, and what is scalar product. In this lecture, we learn what is Gram-Schmidt theorem. This deals with orthonormal basis. What is a basis? We know linearly independent vectors in a space or vector space or matrix space. It can be anything. Ortho. So those are all each other orthogonal vectors. Their scalar product is 0. Scalar product, if you see, for example, psi and phi is equal to 0. So orthogonal and their norm is 1. Psi is equal to 1 or phi is equal to 1. So in this theorem clearly defines how to convert a basis vectors, linearly independent basis vectors into orthonormal basis vectors. Orthonormal basis. The procedure is like this: first basis vector, then second basis vector, then all the three basis vectors, all the other basis vectors. First basis vector, first one, we the same vector normalize it or make it unit vector. We can do it by dividing its own length. For example, psi, a vector psi is there. Vector psi. So its length is, we can make it by psi square root of its length psi comma psi. So this is now unit vector or normalized. This is the first basis vector. Second basis vector, we can subtract the projection of so this is the first vector. Second vector is, we can subtract the projection of second vector in first basis vector and renormalize the remaining part. For example, if you take pi, its projection in psi, you have to take it psi phi, and pi is there anyway. So this is the second vector. And like this, we have to subtract in whatever the remaining basis, all the other vectors. We'll see a problem. Then we can understand it clearly how to form from linearly independent basis to orthonormal basis. So Gram-Schmidt theorem discusses or tells us how to form a orthonormal basis. So we'll see some problem. We have vector 1 3, 0, 0. Vector 2, 0, 1, 2. And vector 3, 0, 2, 5. So now from this we convert this basis to orthonormal basis. First vector, just normalize it. So what is the length of this vector? Square root of 3 square plus 0 square plus 0 square. So 3. So length of this vector. So first vector is equal to normalized vector by 3. 1 by 3 of 3, 0, 0. So this will become 1, 0, 0. This is the first normalized vector. First one is I is equal to 1, 0, 0. Then now we'll make it second vector. We'll take second vector. What is second vector? 0, 1, 2. So as per the grams, so second vector is equal to 0, 1, 2. As per the Gram-Schmidt theorem, what is its second vector is 0, 1, 2. So we'll take 0, 1, 2. This is 2 dash 0, 1, 2 minus first vector normalized vector is 1, 0, 0 into its basis. Sorry, it's a scalar bar projection of it into first one. So 1, 0, 0, 0, 1, 2. What is this? 1, 0, 0, 0, 1, 2 is 1, 1, 0, 0. So it is 0. So this is 0. This total value will be, total value is 0, 0, 0, 0, 0. So 0, 1, 2. 1, 0, 0, 0, 1, 2, but we have to normalize it. What is the length of it? Length of it is 0 square plus 1 square plus 2 square. So this is 4 plus 1 root 5. So 2 normalized, 2 or orthonormal 2 is 0, 1 by root 5 and 2 by root 5. So this is the second normalized vector or orthonormal vector. So now we'll have to determine which one, third one. Third one is already know 0, 2, 5. So this also same. This vector 3 dash is equal to 0, 2, 5. minus 1 0 0 into its projection in 0 to 5. Its projection again 1 0 0 0 to 5. So this is again 0. This will be 1 0 1 into 0 0 to 0 into 5. This is completely 0 minus second vector is 0 1 over root 5 2 by root 5 into its projection 0 1 over root 5 2 over root 5 into 0 to 5. So go to next page. 3 dash is equal to 0 to 5 minus 0 minus this one 0 1 over root 5 2 by root 5 into this one. If we see this one, I'll write this also 0 1 over root 5 2 by root 5 into 0 0 to 0 to 5. So this one 0 0 plus 2 by root 5 plus 10 by root 5. 2 2 5 are 10. So totally 10 plus 2 12 by root 5. So this is 0 to 5 minus, so 12 by, this value is 12 by root 5 into this vector. So what is this? 0, 12 by 5, 12 by root 5 into 1 by 5, 24 by 5. So we see this 0 minus 0, 0, 2 minus 12. So 5 2 is 10 minus 12 minus 2 by 5 and then 5 5 is 25, 1 by 5. Then this is the vector, we have to normalize it. So 3 unit vector orthonormalized one is 0, minus 2 by 5, 1 by 5. Zero minus 2 by 5, 1 by 5. So we have to normalize it. What is the length of it? Again 0 square plus 4 by 25 plus 1 by 25. So 5 by 25, that is 1 by root 5. This is equal to 1 by root 5. So what is the, so if you multiply this with 1 by 1 over root 5 into root 5, so it will become 0 minus 2 by root 5 1 over root 5. So this is the one vector, that is the other two vectors are there. So if you write all the, first one is 1 0 0, second one is what is the second one, 0 root 5 2 by root 5, and third one is 0 minus 2 by root 5 1 by root 5. So even if you multiply this, all this with other one, 1 into 2 becomes 0, 1 into 3 becomes 0, 2 into 3 say 0 0, minus 2 by 5 plus 2 by 5 will be 0. So 2 3 becomes 0, 3 1 becomes 0. So all are orthogonal, as well as their length is, if you see 1 by root over 5 plus 2 by root over 5, 1. Here also minus 2 by root 5, 1 by root 5 is 1. So they are orthonormal as well as orthonormal basis vectors. This is the one orthonormal